London, 1940. German bombs rained down upon the city every night, shaking the ground beneath a small laboratory at Oxford where Howard Florey hunched over a row of test tubes, their contents bubbling weakly under dim light. The glass vessels trembled with each distant explosion, threatening to topple from the wooden rack that held them. Ernst Chain stood beside him, his hands gripping the edge of the counter, his voice hoarse as he said, "If this batch fails, we start from zero again." Florey responded quietly, his eyes never leaving the delicate liquid. "And if it succeeds, it will save thousands." A faint blue shimmer reflected in the liquid, catching the overhead bulb's weak glow. Penicillin. They had barely enough for one person. One single human life hung in the balance of this fragile substance they had spent months cultivating in makeshift containers throughout the basement laboratory. They chose a policeman dying from blood poisoning, a man named Albert Alexander whose wife waited in the corridor outside, and for a brief moment, a miracle unfolded before their eyes. The fever dropped hour by hour. The wounds began to heal. Pink tissue replacing the angry red of infection. Hope flickered to life in the sterile room, spreading from Florey to Chain to every nurse who witnessed the transformation. Then darkness returned like a wave crashing over them all. The medicine ran out. Production could not keep pace with need. The patient died. Florey stood motionless in the hospital corridor, hot tears forming behind his spectacles as he whispered to no one in particular, "We have seen the miracle. Now we must learn to multiply it." Cut to New York City, 1943. Inside a converted ice factory in Brooklyn, now owned by Pfizer, enormous fermentation tanks churned and bubbled, their steel surfaces warm to the touch, while thousands of workers labored through the night without rest, their faces illuminated by the glow of monitoring equipment. The air was thick with the smell of fermenting corn and growing fungus. Normandy, 1944. A military physician whose uniform bore the name Connor injected penicillin into a wounded soldier's arm as artillery fire rumbled in the distance. By the following morning, the young man opened his eyes again, asking for water, asking about his platoon. In war, the most miraculous thing was not a weapon. It was the belief that human beings could still save one another, that amid the machinery of death, the machinery of life could still function. Golden light filtered through layers of smoke drifting across the English Channel. A single drop of medicine rolled from the tip of a needle, falling downward, beginning a journey that would save 150,000 lives. September 1928. Inside a cluttered laboratory on the second floor of St. Mary's Hospital in London, Alexander Fleming returned from a summer holiday in Scotland to find his bacterial cultures contaminated with mold. The petri dishes sat on his workbench exactly where he had left them weeks earlier, now sporting fuzzy colonies of various colors. Most scientists would have discarded the ruined cultures immediately, cursing their carelessness for leaving them exposed. Fleming paused. He was known among colleagues for his careful observation, his tendency to notice what others overlooked. Around one particular mold, the bacteria had died. The zone of death formed a perfect circle, as if something invisible had drawn a protective barrier around the fungal colony. Fleming leaned closer, adjusting his spectacles, his curiosity awakening like a flame catching dry wood. The mold was Penicillium notatum, a common fungus that grew on bread, fruit, and damp walls throughout London. The substance it produced, which Fleming would name penicillin after the genus of mold, had killed the Staphylococcus bacteria surrounding it. He spent the following month studying the phenomenon. He grew more cultures, tested the mold's effects on different bacterial species, attempted to isolate the active compound. The substance was maddeningly unstable, breaking down within hours of extraction. It was difficult to produce in any quantity. Fleming was a bacteriologist, not a chemist. He lacked the expertise to purify and concentrate the active ingredient. But he recognized its potential, an antibacterial substance produced by a living organism, harmless to human tissue, capable of killing deadly bacteria. If it could be harnessed, it might revolutionize medicine. He published his findings in the British Journal of Experimental Pathology in 1929. The paper was titled, "On the Antibacterial Action of Cultures of a Penicillium, with special reference to their use in the isolation of B. influenzae. It received little attention. A handful of researchers read it, noted the findings, and moved on. The substance was too unstable, too difficult to work with, too impractical for clinical use. One by one, scientists who might have pursued the discovery decided it was not worth the effort. Fleming himself gradually shifted his focus to other projects. He continued to produce small amounts of penicillin for use in his laboratory, primarily as a tool to selectively culture certain bacteria, but he made no further attempts to develop it as a therapeutic agent. Penicillin became a footnote in microbiology, a curiosity mentioned in passing during university lectures. The discovery slept in dusty journals for more than a decade, waiting for someone to believe in its promise. 1939. War erupted across Europe like a fire leaping from house to house. German forces invaded Poland. Britain and France declared war on Germany. Within months, the conflict spread. In laboratories throughout England, scientists scrambled to address the most pressing crisis facing the military. Wounded soldiers were not dying primarily from their injuries. They were dying from infections that followed. Bacteria invaded open wounds, multiplying in the bloodstream, releasing toxins, triggering sepsis that no surgeon could stop with scalpel or suture. The death toll climbed steadily. Traditional antiseptics like iodine, mercurochrome, and carbolic acid were too harsh, damaging healthy tissue while failing to eliminate deep-seated infections. Sulfonamide drugs, the first synthetic antibiotics, showed promise but had limited effectiveness and dangerous side effects. Medicine had no adequate answer to battlefield infections. At Oxford University, Howard Florey occupied an office in the Sir William Dunn School of Pathology. He was a methodical Australian pathologist in his early 40s, appointed as the school's professor in 1935. Florey was not given to flights of fancy. He approached research with careful precision, valuing reproducible results over dramatic breakthroughs. In the spring of 1939, he sat in his office reviewing old research papers, searching for anything that might help address the infection crisis he knew was coming. Beside him, Ernst Chain worked through a stack of journals. Chain was a brilliant Jewish biochemist who had fled Nazi Germany in 1933, settling in England where his expertise in enzymes and chemical isolation had earned him a position at Oxford. He was temperamental, passionate, prone to heated arguments. Everything Florey was not. Yet the two men worked well together, each balancing the other's weaknesses. Chain flipped through the British Journal of Experimental Pathology and found Fleming's 1929 paper on penicillin. He read it aloud, his accent still carrying traces of his Berlin childhood. Florey listened without interruption, his expression unchanging, his fingers steepled beneath his chin. When Chain finished reading, Florey sat silent for a long moment. Then he said simply, "This could be the light we have been looking for. If the substance truly kills bacteria without harming tissue, it would be exactly what we need." They assembled a small team over the following months. Norman Heatley, a resourceful young biochemist with a gift for improvisation, joined them first. Heatley was quiet, practical, the kind of man who could look at a problem and immediately envision 3 different solutions using whatever materials were at hand. Edward Abraham, a chemist, came next, bringing expertise in organic compounds. Jim Kent, Arthur Gardner, and several research assistants rounded out the group. They had no significant funding, no sophisticated equipment beyond what the university could provide, and no assurance that Fleming's decade-old discovery could be transformed into anything useful. But they had something more valuable than money or machinery. They had certainty that the work mattered, that somewhere in that forgotten paper lay the key to saving lives. The laboratory they established was located in the basement of the pathology building, a space that had previously served as a storage area for old equipment and broken glassware. It was cramped, poorly ventilated, lit by a few bare bulbs hanging from the ceiling. The walls were bare brick, cold and damp. Britain was at war by the time they began work in earnest. Resources were scarce, Scientific supplies were diverted to weapons manufacturing, to radar development, to code-breaking efforts. Glass tubing, rubber hoses, chemicals, culture, media, everything they needed was in short supply. Florey and his team worked with what they could scavenge from other departments, from hospital surplus, from their own ingenuity. Norman Heatley proved to be a genius of improvisation, a man who could transform trash into treasure. He repurposed ceramic hospital bedpans as culture vessels because they were the right size and shape for growing mold. He converted milk bottles and jam jars into fermentation containers, sealing them with cotton plugs. He rigged up an extraction system using old bathtubs, ceramic pots, pie tins, and salvaged piping to separate penicillin from the liquid in which the mold grew. The apparatus looked like something from a plumber's workshop combined with a medieval alchemist's den. Rubber tubes snaked across tables. Glass bottles hung suspended over Bunsen burners. The smell of growing fungus permeated everything. Yet within this chaotic space, something extraordinary began to take shape. Growing penicillium mold required infinite patience. The fungus thrived on a specific nutrient mixture that Heatley developed through trial and error. Temperature had to be maintained within a narrow range. Oxygen levels needed careful monitoring. The slightest contamination from other microorganisms could ruin an entire batch. Heatley experimented with different formulas, adjusting the ratios of glucose, minerals, and nitrogen sources. He tested different strains of penicillium, searching for varieties that produced more of the active substance. The team filled every available surface with containers of growing mold. Bedpans lined the shelves. Bottles covered the tables. The basement smelled of damp earth, fermentation, and fungal growth. Outside, air raid sirens wailed across Oxford. Bombs fell on London and other cities. The world was tearing itself apart. Inside the basement, the scientists tended their fragile cultures as if nurturing seedlings in a garden under siege. Extracting penicillin from the mold proved even more difficult than growing it. The substance existed in minute quantities within the fungal broth, perhaps 1 part per million. It was chemically unstable, breaking down rapidly at room temperature, destroyed by heat, neutralized by acids. Heatley developed a painstaking method of freeze-drying the liquid to concentrate it, then dissolving the residue in a solvent, filtering out impurities, and repeating the process multiple times. Each step reduced the volume while increasing the concentration of penicillin. The process took days of continuous work. A single batch might yield only enough penicillin to treat one infection for 1 day. The team worked in shifts around the clock, sleeping on cots in the laboratory when exhaustion overtook them. Their hands became stained with chemicals. Their eyes grew red from lack of sleep. But slowly, painfully, they learned to produce penicillin in quantities sufficient for testing. Ernst Chain worked on understanding the chemical structure and mechanism of action. He wanted to know precisely how penicillin killed bacteria without harming human cells. His laboratory notebooks filled with diagrams of molecular structures, equations calculating enzyme interactions, theories about cell wall synthesis. Chain was temperamental, often clashing with Florey over methodology and priorities. He wanted to understand everything before proceeding. Florey wanted results quickly, even if understanding came later. Their disagreements sometimes erupted into shouting matches in the laboratory, voices echoing off the brick walls. Yet their conflicts sharpened the research. Florey's calm pragmatism balanced Chain's intense intellectualism. Each pushed the other to think differently, to question assumptions, to try new approaches. By early 1941, the Oxford team had accumulated enough penicillin for their first human trial. The decision of who would receive it carried enormous weight. They needed a patient sick enough that conventional treatment had failed, yet stable enough to survive the experimental procedure. The hospital administration helped them find a suitable candidate. His name was Albert Alexander, a 43-year-old police constable from Oxford. Alexander had scratched his face on a rose thorn while working in his garden several months earlier. The minor wound became infected. He ignored it at first, thinking it would heal on its own. It did not. Bacteria entered his bloodstream through the scratch. By the time he sought medical attention, the infection had spread throughout his body. Doctors admitted him to Radcliffe Infirmary in January 1941. Abscesses covered his face and scalp, oozing pus. His left eye had been surgically removed to prevent the infection from spreading to his brain. His lungs labored with each breath. Fever consumed him, spiking above 105 degrees. He drifted in and out of consciousness. Traditional treatments, sulfonamide drugs, surgical drainage of abscesses had all failed. Alexander was dying. On February 12, 1941, Fleury and his team administered the first dose of purified penicillin to a human patient. They gathered in Alexander's hospital room, a small space with white walls and a single window overlooking a courtyard. Alexander lay in bed, barely conscious, his breathing shallow. Fleury held the syringe, checking it one final time before inserting the needle into a vein in Alexander's arm. The liquid was slightly cloudy, pale yellow. He injected it slowly and withdrew the needle. They waited. Nothing happened at first. Alexander's breathing remained labored. His fever burned on. The medical staff exchanged uncertain glances. Then, slowly over the course of hours, something changed. The fever began to drop. By evening, Alexander's temperature had fallen 2 degrees. By the following morning, he was conscious and coherent. He recognized his wife when she entered the room. He asked for water. He spoke in complete sentences. Within 24 hours, the transformation accelerated. Alexander's abscesses began to drain and heal. The angry red inflammation surrounding his wounds faded to pink. His fever continued dropping. Within 48 hours, he was sitting up in bed, eating solid food, conversing with nurses. The change was so dramatic that word spread through the hospital. Doctors who had written Alexander off as terminal now gathered outside his room, peering through the doorway in disbelief. Nurses whispered about a miracle drug. Fleury remained cautious, documenting every detail, monitoring Alexander's vital signs constantly, but hope kindled in his chest for the first time in months. Chain visited the bedside twice daily, his skepticism gradually transforming into wonder. For 4 days, the improvement continued without interruption. Alexander gained strength. Color returned to his face. He spoke of going home, of returning to work, of seeing his children grow up. The Oxford team celebrated quietly in the basement laboratory, allowing themselves to believe they had succeeded. But beneath the celebration lurked a terrible problem that none of them could solve. Their supply of penicillin was nearly exhausted. They had used almost everything they had produced over the past months to treat Alexander. Production could not keep pace with the needs of even a single patient. Heatley and the others worked frantically to produce more, growing mold in every available container, extracting and purifying around the clock. But it was not enough. The supply ran out. In desperation, they resorted to an unorthodox method. Penicillin passed through the human body largely unchanged, excreted in urine. They collected Alexander's urine in containers, extracted the penicillin from it, purified it as best they could, and re-administered it to him. The practice was distasteful, even degrading from a scientific standpoint, but they had no alternative. Every drop of penicillin was precious. Every dose might buy Alexander another day of life, but the recycled supply was limited and of lower quality. It could not sustain the treatment indefinitely. Without a continuous supply of fresh penicillin, the infection returned. Alexander's condition stabilized for a few days, hovering between improvement and decline, then began to deteriorate. The fever spiked again, climbing back above 100 degrees. Abscesses reappeared on his face. His breathing grew labored once more. The bacteria, temporarily suppressed, multiplied, and spread. On March 15, 1941, 1 month after the treatment began, Albert Alexander died. His wife sat beside his bed, holding his hand as his breathing slowed and stopped. The nurses who had witnessed his brief recovery stood silent in the corridor. Fleury stood outside the hospital room after Alexander's body had been taken away, staring at the closed door, unable to move. Tears blurred his vision, turning the white walls into shapeless masses of light. Chain found him there 30 minutes later, equally devastated. They had seen the power of penicillin with their own eyes. They had watched a dying man return to life, had spoken with him, had seen hope return to his wife's face, and they had lost him because they could not produce enough medicine. The tragedy burned itself into their minds like a brand. Florey spoke quietly, his voice shaking, barely audible above the sounds of the hospital around them. "We know it works. Now we must find a way to make it in quantities that matter. We cannot let this happen again." The team treated several more patients over the following months, learning from Alexander's case. They chose children primarily, whose smaller bodies required less penicillin, making their limited supplies stretch further. A 15-year-old boy with a severe hip infection recovered completely. A 4-year-old girl with meningitis survived against all odds. A 6-year-old boy with septicemia pulled through. These successes validated the treatment, but they also highlighted the cruel mathematics of scarcity. Every child they saved meant an adult they could not treat. Every dose given to one patient was a dose unavailable to another. The evidence was undeniable. Penicillin could cure bacterial infections that were otherwise fatal, but Britain lacked the industrial capacity to manufacture it in meaningful quantities. The country's factories were producing aircraft, tanks, artillery shells, and ammunition. Steel, rubber, chemicals, labor, everything was directed toward the war effort. There was no room for experimental medicine, no capacity to spare for manufacturing a drug whose benefits, however dramatic, remained unproven at large scale. Florey made a decision that would change everything. He would take the discovery to America. The United States had not yet entered the war. Its industrial infrastructure remained intact, its factories not yet converted to military production. American pharmaceutical companies had resources British firms lacked. If Florey could convince them of penicillin's potential, large-scale production might be possible. Chain argued against the plan. He worried about losing control of the discovery, about American companies patenting the process and restricting access. Florey overrode his objections. Saving lives mattered more than questions of credit or profit. In July 1941, Florey and Heatley boarded a transatlantic flight bound for New York. The journey was dangerous. German submarines prowled the Atlantic, and Luftwaffe fighters patrolled the skies over the English Channel. The plane flew a circuitous route to avoid enemy aircraft, stopping in Lisbon and the Azores before crossing the ocean. Florey and Heatley carried with them cultures of Penicillium mold, the most productive strains they had developed, smuggled inside the linings of their coats. If the plane were shot down or if they were searched and the cultures confiscated, everything would be lost. But Florey was willing to take the risk. The future of penicillin depended on keeping the discovery alive and moving it beyond Britain's borders. They landed in New York on a humid summer day and immediately began visiting pharmaceutical companies. Florey had prepared a presentation detailing their research, the clinical results, the potential applications. He and Heatley carried briefcases full of data, photographs of healed patients, chemical analyses. They approached Merck first, then Squibb, then Leaderly. The reception was uniformly cold. Company executives listened politely, asked a few questions, then declined to invest. Penicillin seemed too difficult to manufacture, too uncertain in its returns. The fermentation process was complex. Scaling up from laboratory flasks to industrial tanks presented enormous technical challenges, and there was no guarantee that the drug would work as well in large populations as it had in small trials. War production was profitable. Government contracts for sulfa drugs were already lucrative. Experimental antibiotics were not worth the financial risk. Florey and Heatley moved from city to city, from Philadelphia to Chicago, knocking on doors, presenting their data, facing rejection after rejection. The frustration was maddening. They possessed proof that penicillin saved lives, yet no one seemed willing to take the next step. Finally, they approached the United States Department of Agriculture's Northern Regional Research Laboratory in Peoria, Illinois. The facility was not a pharmaceutical company, but a government research center specializing in finding new uses for agricultural products. Scientists there had developed innovative fermentation techniques for producing various compounds from corn, soybeans, and other crops. Florey explained the situation to the lab's director. If penicillin could be produced on an industrial scale, it would save soldiers' lives in the war that America seemed increasingly likely to enter. It might change the outcome of battles, reduce casualties, shorten the conflict. The director agreed to help. The Peoria lab had expertise in deep tank fermentation, a technique that might solve the production problem. One of their key insights involved the fermentation medium, the liquid in which the mold grew. In Oxford, the team had grown penicillium on a synthetic nutrient solution made from purified chemicals. It worked, but mold growth was slow, and penicillin yields were low. The Peoria scientists suggested using corn steep liquor, a thick, brownish, syrupy byproduct of the corn wet milling process. It was abundant in the American Midwest, inexpensive, and rich in nutrients that promoted rapid microbial growth. They tested the idea, inoculating batches of corn steep liquor with penicillium spores. The results exceeded all expectations. Mold grown in corn steep liquor produced 10 times more penicillin than mold grown on synthetic medium. The discovery was transformative. Suddenly, industrial-scale production seemed achievable. The Peoria laboratory also began a systematic search for more productive strains of penicillium. Not all molds were equally efficient at producing penicillin. The strain Fleming had originally discovered was relatively weak. The strains Heatley had developed at Oxford were better, but still limited. The Peoria team launched a global effort, collecting soil samples, moldy fruit, decaying vegetation from around the world. Military personnel stationed overseas mailed samples back. Agricultural researchers contributed specimens from their collections. Laboratory assistants tested each sample, growing it in culture, measuring penicillin output. Most produced nothing. A few showed modest improvement. Then one day in 1942, a laboratory assistant named Mary Hunt brought in a moldy cantaloupe she had purchased at a local fruit market for her lunch. The golden flesh of the melon was spotted with blue-green mold. Hunt, following the lab's standing protocol, scraped off a sample and cultured it. The mold turned out to be an exceptionally high-yielding strain of Penicillium chrysogenum. It produced more than 200 times as much penicillin as Fleming's original strain. The cantaloupe cost 25 cents. That rotting piece of fruit, purchased on a whim from a market stall, became the foundation for all industrial penicillin production. Every dose of penicillin manufactured over the following decades descended from Mary Hunt's moldy cantaloupe. By December 1941, events overtook their research. The Japanese attacked Pearl Harbor. The United States entered the war. Suddenly, the American government's interest in penicillin intensified from curiosity to urgency. Military planners understood that battlefield infections were killing as many soldiers as combat wounds. In World War I, more American servicemen had died from disease than from German bullets and shells. If penicillin could prevent those deaths, it was as valuable as any bomber, any battleship, any weapon in the arsenal. The War Production Board issued directives. Penicillin production became a national priority. Major pharmaceutical companies were brought into the effort through government contracts that guaranteed profits and provided capital for factory construction. Pfizer, Merck, Squibb, Abbott, and more than 20 other companies received funding to develop large-scale fermentation capacity. The challenge was immense. Growing mold in laboratory flasks was one thing. Cultivating it in 10,000-gallon fermentation tanks was entirely different. Temperature had to be controlled precisely. Oxygen had to be bubbled through the liquid continuously to keep the mold alive. Contamination from unwanted bacteria or fungi could ruin an entire batch worth thousands of dollars. Engineers designed massive stainless steel vats, equipped with cooling coils, stirring mechanisms, and air injection systems. They developed protocols for sterilizing equipment, for monitoring fermentation progress, for extracting and purifying the final product. It was a collaboration between biologists, chemists, and mechanical engineers unlike anything attempted before. Pfizer took the lead in production. The company had experience with fermentation technology from producing citric acid and converted a former ice factory in Brooklyn, New York, into a penicillin manufacturing facility. The building was enormous, 5 stories tall, occupying an entire city block. Workers installed rows of fermentation tanks on each floor, connecting them with miles of piping. The tanks stood 12 feet tall, made of gleaming steel, each capable of producing millions of units of penicillin per batch. The air inside the factory was humid and warm, thick with the smell of fermenting corn and growing fungus. Technicians in white coats monitored gauges and valves around the clock, adjusting conditions to optimize mold growth. It was relentless work. A single mistake, a moment of inattention, could contaminate a tank and waste days of production. But the system worked. Within months of opening, the Brooklyn plant was producing more penicillin per week than the entire Oxford laboratory had produced in 2 years. The first large batches of American-produced penicillin were shipped to North Africa in early 1943, where Allied forces under General Eisenhower were engaged in fierce combat against German and Italian troops. Military physicians received the new drug with a mixture of hope and skepticism. They had seen too many miracle cures fail in practice. Too many treatments that worked in laboratories proved useless on battlefields. But orders were orders. They began administering penicillin to wounded soldiers, injecting it directly into bloodstreams or packing it into infected wounds. Lieutenant Connor was an army doctor stationed near Tunis with the 1st Infantry Division. He was 32 years old, from a small town in Ohio, trained at Johns Hopkins before the war. In March 1943, he received his first shipment of penicillin, a wooden crate containing 24 small vials packed in ice. He read the instructions, which were minimal. Inject intravenously every 3 to 4 hours. Monitor for adverse reactions. That was all. No detailed protocols, no extensive clinical data, just a directive to use it and report results. A young private arrived at the field hospital that afternoon with a gunshot wound to the abdomen. Shrapnel from an exploding shell had torn through his uniform and into his gut. Surgeons removed the fragments, cleaned the wound as best they could, sutured the damaged intestine, but infection had already set in. The soldier's fever climbed above 104 degrees. His pulse raced. His skin grew clammy. Connor had seen this pattern dozens of times. It almost always ended in death. He prepared a syringe of penicillin, dissolved the yellow powder in sterile water, found a vein in the soldier's arm, and injected it slowly. Then he waited. By the next morning, the fever had broken. The soldier was conscious, thirsty, asking for water. His pulse had normalized. The wound, which had been angry and inflamed the previous day, looked cleaner, less swollen. Connor could hardly believe it. He injected penicillin into another patient, a corporal with a compound fracture and severe tissue infection. The same result. Then a sergeant with pneumonia. Another recovery. With each success, Connor's skepticism transformed into amazement. He wrote detailed reports, documenting every case, every dose, every outcome. Word spread through the medical corps like wildfire. Penicillin worked. It worked consistently. It worked miraculously. Infections that would have required amputation resolved with treatment. Soldiers who would have died walked out of field hospitals days later. Back in Oxford, Howard Florey received a telegram in April 1943. It came through military channels, delayed by censorship and routing. 2 words written in capital letters. IT works. No explanation, no details, just those 2 words. Florey read the message 3 times, standing in his office, the paper trembling slightly in his hands. Then he sat down heavily in his desk chair, removed his spectacles, and covered his face with his hands. Tears streamed down his cheeks, soaking into his palms. He wept silently for several minutes, releasing months of tension, doubt, and fear. Ernst Chain found him there when he came to discuss the day's experiments. Chain read the telegram, still lying on the desk, and understood immediately without needing to ask. They had done it. The forgotten discovery had become a lifeline stretching across oceans and battlefields. But success brought a new crisis almost immediately. Demand for penicillin exploded beyond anyone's projections. Every military hospital requested it. Every field surgeon demanded supplies. Every medic wanted vials in his pack. Production, despite massive industrial efforts, could not keep pace. Pharmaceutical companies operated factories at maximum capacity 24 hours a day, but it was not enough. Soldiers waited for treatment, knowing that penicillin existed somewhere, knowing that it could save them, but unable to access it because supplies had not arrived or had been diverted elsewhere. Some died waiting, succumbing to infections that could have been cured if only the medicine had been available hours or days earlier. The shortage led to extraordinary measures that would have been unthinkable in peacetime. Military hospitals began implementing the same desperate practice Fleury's team had used with Albert Alexander. Nurses collected the urine of patients who had received penicillin injections. The drug passed through the kidneys largely intact, excreted in urine within hours of administration. It could be extracted from urine through chemical processes, purified to some degree, and reused. The practice was distasteful, embarrassing even. Nurses and doctors hated doing it. Patients felt humiliated, but it saved lives. Every drop of penicillin mattered. Every dose that could be recycled meant another soldier might survive. Medical personnel learned to overcome their disgust and do what was necessary. Ernst Chain was appalled when he learned what was happening in military hospitals. He confronted Fleury in the Oxford laboratory one evening, his voice rising with anger and indignation. "We are desecrating science itself. We are treating a profound medical breakthrough like scrap metal to be melted down and recast. This is beneath us. This degrades everything we have worked for. We should be producing enough penicillin that such measures are unnecessary." Fleury looked at him steadily across the cluttered laboratory bench, his expression calm but his eyes tired. "If it saves a life, then it is science in its truest form. We do not have the luxury of pride or dignity. We do what works. Production will increase. Factories are being built. Methods are improving. But until then, we use every resource available. That is not degradation. That is determination." Chain fell silent, unable to formulate a response. He knew Fleury was right. Logic and necessity outweighed aesthetic concerns, but the weight of it, the relentless pressure, the knowledge that people were dying because they could not solve production problems fast enough, wore on them all. The celebration they had felt upon receiving confirmation that penicillin worked gave way to exhaustion and renewed urgency. By spring 1944, production had increased substantially. New factories came online. Fermentation techniques improved. Yields per batch increased as scientists learned to optimize growing conditions. The United States was producing billions of units of penicillin per month, but demand continued to outpace supply because Allied forces were preparing for the largest amphibious invasion in history. Operation Overlord, the invasion of Normandy, would land tens of thousands of soldiers on the beaches of northern France. Casualties were expected to be catastrophic. Every estimate suggested that thousands would die from their wounds or from subsequent infections unless medical supplies were adequate. The Military Medical Command made penicillin a top priority. Factories operated triple shifts. Workers who had been producing penicillin for months were pushed to produce more. Trains carried crates of sealed vials to ports along the Atlantic coast where ships waited to transport them across the ocean to England. On June 6, 1944, Allied forces stormed the beaches of Normandy. Soldiers waded ashore through chest-deep water under withering machine gun fire. Many fell before reaching the sand. Medics waded through the carnage, dragging wounded men to cover, applying bandages, injecting morphine, and for the first time in military history, they carried penicillin in their medical kits, alongside the traditional supplies. In makeshift field hospitals set up in abandoned houses and barns behind the front lines, surgeons operated continuously for days. They extracted bullets and shrapnel, amputated shattered limbs, sutured torn flesh, and after each surgery, they injected penicillin directly into the patient's bloodstream or packed penicillin powder into wounds before closing them. Infections that would have turned gangrenous were stopped before they could establish themselves. Amputations that would have been necessary to prevent sepsis from spreading were avoided because the antibiotic controlled the bacteria. Soldiers who would have died from post-operative infections survived and eventually returned home. The statistics compiled after the Normandy campaign were staggering. During World War I, infection had killed more soldiers than combat injuries. The ratio was roughly 3 deaths from disease for every 2 from enemy action. In World War II, thanks primarily to penicillin, that ratio reversed. Fewer soldiers died from infection than from their wounds. The survival rate for wounded soldiers increased by more than 40% compared to the previous war. Penicillin saved an estimated 100,000 lives during the Normandy campaign alone. By the end of the war in Europe, the total number of lives saved by penicillin exceeded 150,000. The drug became known as the wonder drug, spoken of with reverence by soldiers and civilians alike, as if it were not medicine but magic extracted from the earth. In laboratories, factories, and hospitals across the Allied nations, the people who had made it possible continued working without recognition or celebration. Norman Heatley remained at Oxford, refining extraction methods, developing new techniques for measuring penicillin potency. Workers at Pfizer's Brooklyn plant operated fermentation tanks through exhaustion, taking pride in every batch that left the facility. Military physicians like Lieutenant Connor administered injections in blood-soaked field hospitals, documenting outcomes, learning which infections responded best to treatment. They were the unseen architects of survival, the individuals whose combined efforts transformed a laboratory curiosity into a medical revolution. By the time the war ended in 1945, penicillin production had reached industrial scale beyond anything Florey had imagined in that Oxford basement. American factories alone were producing over 600 billion units per month. The substance that had once required weeks to produce enough for a single patient now flowed from production lines in quantities sufficient to treat millions. The transition from scarcity to abundance happened in less than 4 years, a testament to what human ingenuity could accomplish when necessity demanded it. In October 1945, the Nobel Prize in Physiology or Medicine was awarded jointly to Alexander Fleming, Howard Florey, and Ernst Chain. The announcement came from Stockholm on a gray autumn morning. Fleming received the news in his laboratory at St. Mary's Hospital, where he continued his research into bacteriology. Florey heard while working late in Oxford, reading the telegram by lamplight. Chain was at home when a colleague telephoned with the information. The 3 men would share one of science's highest honors for their roles in developing penicillin. The award ceremony was held in Stockholm in December. Fleming traveled from London. Florey and Chain came from Oxford. They wore formal evening dress, black tailcoats and white bow ties, and sat in the ornate hall among Swedish royalty and distinguished scientists from around the world. When Fleming's name was called first, the applause was thunderous and prolonged. He stood, acknowledged the ovation with a slight bow, and walked to the stage to receive his medal and certificate. Cameras flashed. Reporters scribbled notes. Fleming had become the public face of penicillin, the lone scientist whose chance observation had changed medicine forever. Newspapers had published his photograph for months. Magazine articles recounted the story of his discovery in dramatic terms, portraying him as a hero of science. When Florey's name was announced, the applause was polite but noticeably briefer. He rose, walked to the stage with his characteristic calm demeanor, accepted his award, and returned to his seat. Chain's reception was similar. The audience recognized their contributions but reserved its enthusiasm for Fleming. The disparity was subtle but unmistakable. In the public imagination, Fleming had discovered penicillin. Florey and Chain had merely helped develop it. The nuance of their respective contributions was lost in the simplification necessary for popular storytelling. Over the following months, Fleming became a celebrity. He gave lectures to packed auditoriums. Universities awarded him honorary degrees. Governments bestowed medals and honors. He appeared on the cover of Time magazine. The narrative that formed around him was compelling and easily understood. A solitary genius, working in his laboratory, noticed something others had overlooked. His powers of observation and scientific intuition led to one of the greatest medical breakthroughs in history. It was a story that fit the public's understanding of how science worked. Florey and Chain, by contrast, remained largely unknown outside scientific circles. Their work was harder to explain, less dramatic, more collaborative and incremental. They had taken Fleming's observation and transformed it into practical medicine through years of painstaking research. They had solved problems of extraction, purification, production, and clinical application. They had convinced governments and companies to invest resources. They had designed the methods that made mass production possible. But these contributions did not make for compelling newspaper stories. The public wanted heroes, not teams. It wanted moments of inspiration, not years of grinding effort. Chain struggled with the injustice of it. He had spent years working on penicillin, sacrificing his health, his personal life, everything to make it viable. He had solved chemical problems that Fleming had not even attempted. He had shared the Nobel Prize equally, yet he was treated as a footnote in Fleming's story. The bitterness grew in him like a cancer. One evening in the hotel in Stockholm, after the official ceremonies had concluded, Chain confronted Florey in their shared suite. The two men had been drinking whiskey, trying to relax after days of formal events and tedious social obligations. "They do not see us," Chain said, his voice tight with anger. "They do not understand what we sacrificed." Fleming made an observation. A valuable observation, yes, but only an observation. We made a medicine. We took his curiosity and transformed it into something that saves lives. Why are we footnotes in our own story? Why does he receive all the glory? Florey poured 2 more glasses of whiskey and handed one to Chain. He sat down heavily in an armchair, loosening his bow tie, his face showing the exhaustion he had hidden during the public events. "Because stories need heroes," he said quietly. "And heroes need to be simple. Fleming is easy to understand. A lone scientist, a chance discovery, a happy accident. People can relate to that. We are complicated. A team, a process, 1,000 small decisions that no one outside our field can follow or appreciate. The world prefers myths to reality. Myths are cleaner, more satisfying." Chain drank, the whiskey burning his throat. "Does it bother you that he receives credit for our work?" Florey looked out the window at snow falling over Stockholm, the flakes swirling in the glow of street lamps. He was quiet for a long time before answering. "No, I did not do this work for recognition or fame. I did it because people were dying and I believed we could stop it. We did stop it. 150,000 soldiers lived who would have died. Countless more will live in the years to come because penicillin exists. That is enough. That is more than enough. The world can celebrate Fleming if it wishes. I know what we accomplished. You know. The soldiers who lived because of us know. Even if they never learn our names. History will sort out the details eventually. Our work speaks for itself." Chain wanted to argue, wanted to rage against the unfairness, but he could not. Florey was right. The work had always been bigger than any individual. Saving lives mattered more than receiving credit, yet the knowledge did not ease the sting entirely. Chain would carry that bitterness for years, mentioning it in interviews decades later, always careful to clarify his role, to explain what he had contributed, to ensure that history understood the full story. Florey never spoke of it again. He returned to Oxford after the Nobel ceremony and resumed his research as if nothing had changed. Fleming, for his part, accepted the adulation with grace. He gave credit to Florey and Chain in his lectures and writings, always acknowledging that they had made penicillin practical, but the public attention remained focused on him. He could not control how the story was told, and he did not try very hard to redirect it. He was human after all, and the recognition was gratifying after years of obscurity. The years after the war brought new challenges and new discoveries. Penicillin's success inspired the search for other antibiotics. Researchers around the world began screening soil samples, testing fungi and bacteria, looking for other organisms that produced antibacterial compounds. Streptomycin was discovered, effective against tuberculosis. Chloramphenicol followed. Then tetracycline, erythromycin, and dozens of others. The antibiotic era had begun. Diseases that had killed millions for millennia became treatable. Life expectancy increased dramatically. Infant mortality dropped. Surgery became safer. Medicine was transformed more profoundly in 2 decades than in the previous 2 centuries. But success also bred complacency and misuse. Doctors prescribed antibiotics for viral infections where they were useless. Patients took partial courses and stopped when they felt better, allowing resistant bacteria to survive and multiply. Farmers added antibiotics to animal feed to promote growth, creating reservoirs of resistant organisms. By the 1960s, reports of antibiotic-resistant bacteria began appearing in medical journals. Strains of Staphylococcus emerged that penicillin could not kill. Gonorrhea bacteria developed resistance. Tuberculosis strains appeared that survived multiple antibiotics. The miracle drugs were losing their power. Fleming himself warned about this possibility in his Nobel Prize acceptance speech. "The time may come," he said, "when penicillin can be bought by anyone in the shops. Then there is the danger that the ignorant man may easily underdose himself, and by exposing his microbes to non-lethal quantities of the drug make them resistant." His words proved prophetic. The misuse of antibiotics created selective pressure that favored resistant bacteria. Evolution worked rapidly in microbial populations. Organisms that could survive antibiotic exposure thrived and spread their resistance genes. The arms race between medicine and microbes continued, with bacteria adapting faster than new drugs could be developed. Yet despite these emerging challenges, penicillin's legacy remained profound. It had proven that infectious diseases were not inevitable acts of God but solvable problems, amenable to human intervention. It had shown that international scientific collaboration could achieve results impossible for any individual or nation alone. British scientists had made the discovery. American industry had scaled production. Soldiers from dozens of countries had benefited. The achievement belonged to no single person or place but to humanity as a whole. Howard Florey continued his research at Oxford until his retirement, focusing on antibiotics, inflammation, and cellular biology. He became provost of Queen's College, served as president of the Royal Society, received countless honors including a knighthood and later a life peerage, becoming Baron Florey of Adelaide and Marston. He died in 1968 at the age of 69 from a heart attack. His funeral was attended by colleagues and former students, but the general public barely noticed his passing. The newspapers that had celebrated Fleming's death 4 years earlier gave Florey only brief obituaries. Ernst Chain continued his career with distinction, working in Italy and later returning to England to establish a new biochemistry department at Imperial College London. He remained prickly about credit for penicillin throughout his life, giving interviews in which he carefully delineated who had contributed what. He advocated for stronger patent protections for pharmaceutical discoveries, arguing that the failure to patent penicillin had cost Britain billions in potential revenue. He died in 1979 at the age of 73, leaving behind a legacy of scientific achievement and a reputation for brilliance tempered by difficult personality. Norman Heatley, the quiet genius who had solved so many practical problems, received almost no public recognition during his lifetime. He remained at Oxford, continuing research and teaching, never seeking attention, never complaining about his anonymity. In 1990, more than 4 decades after penicillin's development, Oxford University finally awarded him an honorary doctorate in medicine, the first such degree the university had granted in its 800-year history. Heatley was 82 years old. He accepted the honor with characteristic modesty, saying simply that he had enjoyed the work and was glad it had proven useful. He died in 2004 at the age of 92. Mary Hunt, whose moldy cantaloupe had provided the most productive penicillium strain, returned to obscurity immediately after her contribution. No one thought to celebrate a laboratory assistant who had simply brought her lunch to work. She continued working at the Peoria laboratory for several more years before leaving science entirely. Researchers who later wrote histories of penicillin often struggled to find information about her. She was a footnote to a footnote, a reminder that great achievements rest on countless small contributions from people whose names are never recorded. Decades later, in hospitals around the world, Penicillin and its descendants continued saving lives every day. A child with strep throat received amoxicillin and recovered in days instead of dying from rheumatic fever. An elderly woman with a urinary tract infection took a course of antibiotics and avoided sepsis. A young man injured in a car accident received prophylactic antibiotics after surgery, and his wounds healed without complication. These small miracles happened millions of times each year, so commonplace that no one remarked on them. The drama had faded. The wonder had become routine. Medicine had advanced to the point where bacterial infections, once the leading cause of death, were considered minor inconveniences. Yet behind every injection, every pill, every recovery, lay the story of those who had made it possible. The story of Fleming's observation and the decade it spent forgotten. The story of Fleury's determination to resurrect an abandoned discovery. The story of Chain's chemical genius and Heatley's practical improvisation. The story of American researchers who screened thousands of mold samples. The story of factory workers who operated fermentation tanks through the night. The story of military physicians who injected the first doses into wounded soldiers. The story of soldiers who lived and soldiers who died waiting for supplies. The story of a cantaloupe purchased for 25 cents. The story of urine collected in bedpans. The story of tears shed over a dead policeman. The story of a telegram that said only it works. All of these stories woven together into the fabric of modern medicine. In 2015, a young physician named Sarah Mitchell stood in a hospital room in Seattle preparing to inject penicillin into a 7-year-old girl named Emma, who had developed bacterial meningitis. The child lay in bed connected to monitors, her mother sitting beside her holding her hand. Dr. Mitchell explained the treatment in simple terms. This is an antibiotic called penicillin. It will kill the bacteria causing the infection. She should start improving within 12 to 24 hours. The mother nodded, trusting without fully understanding. Dr. Mitchell did not tell the mother about Alexander Fleming, about Howard Fleury, about Ernst Chain. She did not mention the basement laboratory at Oxford, the fermentation tanks in Brooklyn, the soldiers on Normandy beaches. She did not explain that the medicine in her hand represented one of humanity's greatest achievements, a triumph of observation, determination, collaboration, and industrial scale unprecedented in history. She simply prepared the injection, found a vein in Emma's small arm, and administered the dose. The mother watched anxiously. Emma barely stirred, already deep in fever. By the following morning, Emma's fever had broken. By afternoon, she was awake and asking for her favorite stuffed animal. By the second day, she was sitting up, eating, complaining that she wanted to go home. By the third day, the doctors declared her out of danger. She was discharged a week later, fully recovered, ready to return to school and her friends and her normal life. Her mother cried with relief and thanked Dr. Mitchell profusely. The doctor smiled and said it was just doing her job. No one mentioned the word miracle. It was simply what antibiotics did, but it was a miracle nonetheless. A quiet miracle, repeated millions of times across the globe, made possible by people who believed that human beings could save one another even in the midst of war. A miracle built on chance observation and determined effort, on forgotten papers and desperate improvisation, on industrial might and medical courage. A miracle that began with a single drop of liquid shimmering blue under laboratory light and grew to encompass the world. The story of penicillin is not merely the story of a drug. It is the story of what humans can accomplish when they choose creation over destruction, when they value life over pride, when they collaborate across borders and disciplines toward a common goal. It is a story about the power of persistence, about refusing to accept that suffering is inevitable, about believing that solutions exist even when they seem impossible. In the final analysis, penicillin saved 150,000 lives during World War II. That number, impressive as it is, represents only a fraction of its ultimate impact. In the decades since, antibiotics derived from penicillin, or inspired by its discovery, have saved hundreds of millions of lives. They have made childbirth safer, surgery routine, childhood far less deadly. They have added years to human life expectancy. They have reduced suffering on a scale almost impossible to quantify. Yet the legacy of penicillin extends beyond medicine. It demonstrated that scientific research could produce tangible benefits for humanity, validating public investment in basic science. It proved that wartime necessity could drive innovation that served peacetime prosperity. It showed that international collaboration could achieve more than national competition. It established a model for drug development that continues today. From laboratory discovery through clinical trials to industrial production. Perhaps most importantly, penicillin reminded the world that even in the darkest hours, even when civilization seemed bent on destroying itself, the human capacity for healing remained intact. While bombs fell and armies clashed, scientists in basements grew mold in bedpans. While soldiers died on beaches, factory workers churned out medicine through exhaustion. While nations fought to destroy one another, individuals worked to save anyone they could regardless of nationality. That contradiction, that persistent faith in the value of life even amid mechanized death, stands as perhaps the truest miracle of all. The photograph still exists, preserved in archives at Oxford University. The image shows the research team gathered in their basement laboratory sometime in 1942. Howard Florey stands at the center, calm and focused, a slight smile on his face. Ernst Chain is beside him, gesturing as if making a point. Norman Heatley stands slightly apart, characteristically modest, his attention on something outside the frame. Others fill the space around them, researchers and assistants whose names are mostly forgotten now. The laboratory behind them is cluttered with equipment, jury-rigged apparatus, bottles and tubes and makeshift containers. Golden afternoon light streams through a high window, illuminating dust motes floating in the air, casting the entire scene in warm tones that soften the austere surroundings. They look tired in the photograph. Their clothes are rumpled, their faces showing the strain of long hours and uncertain outcomes. Yet they also look determined, even hopeful. They are people who have seen something extraordinary and believe they can harness it. They are scientists who have glimpsed the future and are working to bring it into being. They do not know yet that they will succeed beyond their wildest projections. They do not know that their names will be remembered or forgotten by history. They know only that the work matters, that lives depend on it, that they must continue regardless of recognition or reward. That photograph captures something essential about the human enterprise of science. It is not glamorous, it is not simple. It does not offer instant gratification or easy answers. It is hard work performed by ordinary people who believe that understanding nature and applying that understanding can reduce suffering. It is collaboration and argument, success and failure, breakthrough and setback, all mixed together in pursuit of knowledge that might prove useful. It is, in other words, the opposite of miracle and magic. It is deliberate, methodical, reproducible, teachable. It is humanity at its best. When the last living members of that Oxford team died, when the factories that produced wartime penicillin were demolished or converted to other uses, when the soldiers who received those first injections passed away from old age, the photograph remained, and the medicine remained, and the legacy remained, not as monument or memorial, but as living practice woven into the fabric of modern life, so completely that it became invisible. Every year, millions of people receive antibiotics without ever thinking about where they came from. Every day, infections that would have been death sentences 80 years ago are cured with a simple prescription. Every moment, somewhere in the world, someone lives who would otherwise have died because scientists in a basement laboratory believed that a forgotten discovery deserved a second chance. That is the wonder. Not the drug itself, but what it represents. The determination to save rather than destroy. The choice to invest in healing rather than accept suffering as inevitable. The recognition that human ingenuity, properly directed, can overcome challenges that seem insurmountable. The understanding that individual genius matters less than collective effort. The faith that life has value worth preserving. A single drop of medicine falling from a needle. A single decision to try again after failure. A single belief that saving one life might lead to saving thousands. These small moments accumulate into transformation. They do not announce themselves with trumpets or fanfare. They happen quietly, in basements and factories and field hospitals. They are performed by people whose names will be forgotten, and they change everything. This is how progress occurs. Not through lone heroes or sudden revelations, but through sustained effort by many hands working toward common purpose. The story of penicillin is the story of what we can accomplish when we remember that truth. When we choose collaboration over competition, persistence over pride, the welfare of strangers over personal glory. When we decide that saving lives matters more than receiving credit. When we believe that human beings, flawed and finite as we are, still possess the capacity to reduce the suffering that has always haunted our species. The war ended. The soldiers came home. The factories shifted to peacetime production. Life continued, altered in ways both profound and subtle by what had been achieved. And in that continuation, in the ordinary routines of existence made possible by extraordinary effort, lies the true measure of success. Not monuments or medals, but the simple fact that people lived who would have died. That children grew up who would have been orphaned. That futures unfolded that would have been stolen. That hope survived even when darkness seemed overwhelming. 150,000 lives, 150,000 futures, 150,000 stories that continued because a few people refused to accept that death from infection was inevitable. That number barely hints at the full impact. How many children were born to those who survived? How many discoveries made, books written, songs sung, love shared, because someone lived past 1944? The ripples spread outward through time, unmeasurable, uncountable, but undeniably real. This is the legacy of penicillin. Not just a drug, but a demonstration of what becomes possible when humanity directs its energies toward preservation rather than destruction. A proof that even in war, even in darkness, the light of reason and compassion need not be extinguished. A reminder that the choice to save rather than destroy remains available in every generation, waiting only for those willing to make it. The photograph fades. The people in it become memories, then legends, then footnotes in textbooks. But what they created endures. Every hospital, every pharmacy, every medicine cabinet contains the evidence of their achievement, and every person who receives an antibiotic inherits their legacy, whether they know it or not. In the end, that is enough. More than enough. It is everything. The quiet continuation of life, the persistence of hope, the knowledge that human beings, when they choose to be, are capable of miracles, not of magic but of science, not of individual genius but of collective effort, not of destruction but of healing. This is what penicillin taught us. This is what that first drop of medicine, falling from a needle in an Oxford laboratory so many years ago, set in motion. And this is what continues, every day. In every place where medicine works to hold back darkness just a little longer, where life triumphs over death one patient at a time, where the legacy of Florey and Chain and Heatley and Fleming and Mary Hunt and all the unnamed others lives on in the simple act of healing. The story ends where it began, with hope, with determination, with the belief that human beings can save one another if they try, and with the quiet satisfaction of knowing that sometimes, against all odds, that belief proves justified. That sometimes the miracle happens, not because of divine intervention or fortunate accident alone, but because people worked until it did. Because they refused to accept failure. Because they believed that life, any life, every life, was worth the effort required to preserve it. This is the story of penicillin. This is the story of 150,000 lives saved during war. But more than that, this is a story about hope itself, about what becomes possible when we choose to act on it, when we transform belief into effort and effort into achievement. When we remember that in the end, there is no greater purpose than reducing suffering, no higher calling than preserving life, no better use of human intelligence than finding ways to heal rather than harm. The drop falls, the needle withdraws, the medicine enters the bloodstream, the bacteria die, the fever breaks, the wound heals, the patient lives, and the world continues, forever changed by those who chose to make it so.